good day. Welcome to the third lecture on acoustic instabilities in aerospace propulsion. In the last class we talked about very basics of acoustics, what is sound, how sound is characterized in terms of frequency, amplitude and so on, and then we spoke about the definition of decibel, and then we talked about various kind of sounds that we hear in our day to day life and what are the typical decibel levels and so on. Then we said that we want to characterize sound, the propagation of sound mathematically. So we are starting from the basic equations of fluid mechanics, which is conservation of mass and momentum and energy and so on, and the state equation. So we derived the conservation of mass, which is the continuity equation, and the momentum equation from basic first principles. We also spoke about the state equation and so on. Today we are going to talk about how we derive the wave equation from these equations. So before I proceed to this, let us start with a story. So there was this professor who was working very late, and then he was trying to go home, and he was, let us say, drunk, and it was something like 3 AM in the morning, and he suddenly discovered that he has lost his or her marriage ring, and then the professor decided to search for the wedding ring. And the professor was searching on the street, and wherever he could, wherever he thought it would be there, and then comes a student, graduate student, who is working very hard, and he saw the professor, and he asked the professor, "Professor, what are you doing? It's so late in the night." Professor said, "I lost my wedding ring and I am searching for it." And the student said, "Okay, let me try to help you. I will join you, and I will try to help you." The student also wanted to impress the professor and so on. So both professor and student are starting to search for the professor's wedding ring. The professor was really worried, because if he or she goes home, the spouse will be very angry. The professor can be a man or a woman, does not matter. And then pretty soon the student discovered that the professor is searching for the wedding ring only under the lamp post. So the student found this very amusing, and he went and asked the professor, "Professor, is there any guarantee that you would have lost the wedding ring? What guarantee is there that you would have lost the wedding ring under a lamp post? It is highly unlikely." The professor said, "Look, I made an assumption. I assumed that the ring will be there under a lamp post." Then the student asked, "I mean, it is a very bad assumption." The professor says, "This is the only place where I can look, so I have made the assumption that it is under the lamp post, so I look where I can." So this is kind of true with our mathematical analysis also, that is, we make assumptions so that we can simplify things and we can deal with things. So often the assumptions are not because they are the way it is so. We make assumptions so that we can do things with the equations, and then we look for situations where the assumptions are applicable, and then we say that the solutions we have derived or the equations we have derived are applicable under these set of conditions and so on. So we derived partial differential equation, and they were coupled partial differential equation, and they were non-linear and so on, and I said that it was very hard to get a very general solution for these things. So the idea is that we need to get some solutions, because we can't just sit there without any hope or helplessly and say that these are complicated equations, we can't do anything about it. So we do the same thing that the professor did. So we can look under the lamp post where we can look. So we make assumptions so that we can solve the equations that we have derived under whatever conditions it is possible. So what we are going to do, let me summarize. What we are going to do is to assume that we have a very small amplitude disturbances, and then we linearize this nonlinear equation, look for a set of linear equations, or somehow simplify this nonlinear equations into a simplified linearized version, and then we try to make more assumptions about the quantities, and then try to see if we can derive some kind of simple linear equation which can be solved with paper and pencil, and that has its own utility no matter how simplifying the assumptions that we have. So in order to refresh your memory, I will write down the equations. this is the conservation of mass or the continuity equation, and the momentum equation is rho times and I want to say that I am doing everything in one dimension, but the 3 dimension is not too difficult. And recall that S naught is constant, that means we are saying that we are talking about a constant entropy process, and now what we need to do is we want to linearize these equations. So you can clearly see the nonlinear term here. This is going to give a lot of trouble in terms of solving the equation, and so what we want to do is to say that the perturbations in pressure, velocity, density and temperature are fairly small compared to the mean values. So we take the equations, perturb the equation around its mean, that way we derived the so called acoustic equations, and then we say that these perturbations are really small. So the advantage of this is that you can actually drop out terms which are product of 2 perturbation quantities, that way you get a linear equation and which we can solve. So this whole process is called linear acoustics. So the assumption here is that perturbations in pressure, density, temperature, velocity are much density are much smaller compared to their mean values. So this would be what we refer to as linear acoustics, and we also assume a homogeneous fluid, and we say that the mean quantities, the mean pressure, mean density and mean temperature are independent of the position of the medium, and we will also say that we are having a quiescent medium, that means there is no mean velocity associated with the medium. So the mean quantities, I will denote the mean by a over bar, p bar, rho bar, t bar are constant and u bar equal to 0. So we have constant thermodynamic mean properties and the mean flow velocity is 0, that means there is a quiescent medium. So we now write all the variables. So let us say pressure equal to we write the variables as a sum of a mean quantity and a fluctuating quantity. Density equal to mean density plus fluctuating density. Temperature equal to T bar plus T prime. U equal to U bar plus U prime. So here we are saying that we have a quiescent medium, so we drop this term, and in general you could have the pressure and mean pressure and density and temperature varying, but in this particular case we are keeping them as constant. We also say that P prime over P bar is much less than 1, rho prime over rho bar, its magnitude is much less than 1, T prime over T bar is much less than 1, and so on. So now so that means if P prime by P bar is much lower than 1 and rho prime by rho bar is much lower than 1, then these quantities are very small, so we can actually drop terms that second order quantity, that means terms that involve products of these quantities. So let us now perturb this equation and write this in terms of this mean and mean quantity and the perturbation quantity, and then try to proceed to linearize the equation. So let us start with continuity equation. So when you linearize this, you will get dou by dou t of rho bar plus rho prime plus dou by dou x of rho bar plus rho prime into u bar plus u prime equal to 0. Now I said that there is no u bar, so we can simply erase this term and just say u prime equal to 0. So let's expand this equation and look at each term. So rho bar is the time average value of time average value of density. So that is an average quantity in terms of time. So by definition it is independent of time. So the first term will drop out. So you keep only dou rho prime by dou t plus, let's expand this term. So we will have dou by dou x of rho bar u prime plus dou by dou x of rho prime u prime equal to 0. Now this is a second order quantity. Of course it is a nonlinear quantity, and the trick here is that we do not want to deal with nonlinearities, we are trying to linearize. So we will drop this. We also assume that rho bar is a constant, it is independent of space, so we can take it outside the derivative. So in the final equations become, so let me say rho bar equal to constant so this would be the perturbation equation for the continuity equation. So it is like the acoustic equations for continuity. So we need to do the same procedure next with the momentum equations. So let us do that. In momentum equation you will have rho bar plus rho prime multiplied by dou by dou t of u bar plus u prime plus u bar plus u prime into dou by dou x of u bar plus u prime equal to minus dou by dou x of p bar plus p prime. So let us simplify matters. We said there is no u bar term, so we can drop wherever there is u bar first, and so let us say rho bar plus rho prime into dou u prime by dou t plus u prime dou u prime by dou x equal to minus, we said that the mean pressure is independent of space, so we can drop the term, and dou p bar by dou x can be dropped, so you will have just dou x. Now let us expand this out, so you will have rho bar dou u prime by dou t plus rho bar u prime dou u prime by dou x plus rho prime dou u prime by dou t plus rho prime u prime by dou x equal to minus dou p prime by dou x. So if you remember, the prime stands for the fluctuating quantity or the acoustic quantity, and once again the bar stands for the mean quantity. So now we look, so this is a first order quantity, we can keep that, so we keep this. This is a second order quantity, we drop this, also a second order quantity, we drop this, is a third order quantity. So let us write, this is second order, this is third order, so we keep only the leading order. So our equation now becomes rho bar dou u prime by dou t equal to minus dou p prime by dou x. So this is the acoustic momentum equation. Next we want to linearize the equation of state. for that, so we said that P equal to P of rho comma S naught, and remember that we said that we are having an isentropic process here. So let us take a graphical approach now. Let us take a look at a graph of P versus rho, and let us say it is varying in some fashion. Let us say let us mark our mean quantity of P bar and rho bar. Let us say this is our mean state, and we perturb things around it. So here this is the region we are looking, in this region. So we although this function could be a general curve, in this small region the pressure is fluctuating about a mean value and density is fluctuating around a mean value, and this is a really small region, and there we can say that this variation is linear. So we have a linear variation. So in the vicinity of this base flow or the mean quantities, we are having a linear variation. So we can write a linear relationship or write equation of straight line. So mathematically we can use a Taylor series, for example. So pressure can be written as can be expanded by a Taylor series about its base value plus dou P by dou rho at constant entropy times rho minus rho bar plus half into dou squared P by dou rho squared into rho minus rho bar whole squared plus higher order terms. So let us throw out the higher order terms and write a keep only the linear term. So we can say, so we drop them. So now we can rewrite this equation as P minus P bar equal to dou rho by dou P by dou rho at S naught times rho minus rho bar. So this would be the linearized equation of state, and if you look carefully we know that this is our P prime and this is our rho prime. So basically we are having P prime equal to dou P by dou rho at constant entropy times rho prime. Now this is a constant value and we can denote it by some constant. So we say that dou P by dou rho, let us call it C squared. This is by definition. So we can say that P prime equal to C squared times rho prime. So at this point it is not clear that C is it is not clear that C is the speed of sound at this point. We will have to wait a little bit before we can see what actually C physically means, whether it is the speed of sound and so on and so forth. So let me summarize the equations that we derived. So let us call this equation 1, call this equation 2, call this equation 3. Now I must say there is something really annoying in the convention used in acoustics, that is if you read any textbooks you keep the primes till some point and then suddenly the author drops the prime. So generally the quantity without prime, so for example rho prime would actually be written as rho, will be written as rho prime sometimes, but P prime is staying as P prime, but if you the mean pressure will be denoted by P bar or something, but after some time so this dropping of primes is sometimes quite annoying, but I will try to be consistent and keep these notations correct. Yeah, thank you. So and in the convention sometimes rho bar is written as rho, and it's very mixed up and so on, but it's better to be consistent and keep the following, keep the same notation about primes and bars, and just keep it. So now what we do is we can, so we next we proceed to derive the wave equation. So what we can do is to take dou by dou t of equation 1 and subtract dou by dou x of equation 2, and then you will get, and we also use p prime equal to c squared rho prime. So if you do that, here you will get, so you are going to get 1 over c squared dou p prime by dou t plus rho bar dou v prime by dou x equal to 0, and here, so if I take a time derivative of this, I will get 1 over c squared d squared p prime by dt squared plus rho bar dou squared u by dou t dou x equals 0. If I take the space derivative of this equation 2, what I will get is rho bar dou squared u prime by dou x dou t equal to minus dou squared p over dou x squared. Now you can subtract this equation from this, subtract the bottom equation from the top equation, and then you can get 1 over c squared d squared p over dt squared equal to dou squared p by dou x squared. So this is the wave equation, or this is the wave equation, or the so-called classical wave equation, and we haven't yet looked at the physical meaning of C, although you might have. I think all of you know that C stands for speed of sound, but we'll have to see very carefully that what C is. So let me, so I must mention that I made an assumption here that dou squared u by dou t dou x equal to dou squared u by dou x dou t. That's why I could subtract the term off or cancel the term out, and of course that's okay when the velocity is a continuous function of x and time, then you can swap the derivatives. So so thus we have derived the wave equation, and let me make a few remarks about the wave equation. We derived the wave equation from fluid mechanics conservation laws. It's just from fundamentals. The second thing I want to say, those of you who are mathematically inclined will notice that this is a hyperbolic partial differential equation. PDE stands for partial differential equation. In fact, you will see that the characteristics are dx by dt equal to plus or minus c. I am not going to go into too much of a detail, but if you are mathematically inclined, you can pursue this line. And we didn't use the linearized equation of energy, but actually if you work out the problem and if you work out the linearized equation of energy, it will turn out that the linearized equation for continuity equation is identical to the linearized equation for energy equation in this case. They may be different in some other cases, that is when you have temperature gradient or when you have combustion and so on, these equations may be different, but right now they are the same. so we see this one dimensional wave equation. We can, I want to make a few more observations. If you do a 3-dimensional derivation of it in 3 dimension, you would have 1 over c squared dou squared p by dou t squared equal to del squared p. In fact, I have started forgetting my primes, so I think this will happen to you also. So please remember to be consistent with the notation, and you can also derive the wave equation in terms of acoustic velocity or velocity potential and so on. You can do this as a homework. So in terms of acoustic velocity, you will also get an identical wave equation. Now I want to speak about certain characteristics of this equation. This is a linear equation. Of course, we linearized our original equation, so naturally we will end up with a linear equation. And this is one of the most studied equations in maths. And in fact, if you had a minus sign here or here, if you had a minus sign, then you know what equation this becomes. It's a Laplace equation which has completely different characteristics. So the advantage of linearity is that if you have linear equation, we'll have linear solutions and we can superpose the solution. So if you have 2 solutions, you can add them or multiply one by a constant, multiply the other by another constant, we can construct more and more solutions. The wave equation is also homogeneous. There are no terms on the there are no other source terms. If there are source term, then the wave equation will become inhomogeneous. So this wave equation does not speak about the production of sound, it only talks about the propagation of sound. We did not consider any sound sources in this, and sound source of course will come in the second half of the course. A similar equation can be derived for the propagation of electromagnetic waves in free space. Of course, it will look slightly different. Similarly, you can also have a wave equation for Schrodinger equation. So this is a very important class of equations that has been well studied by the mathematicians and the physicists. Historically, the 1D wave equation was derived first by D'Alembert for oscillation of strings. And Euler in 1766 derived this equation specifically for sound propagation in fluids. One last comment, the wave equation is a second order partial differential equation and it will have infinite number of solutions. The specific solutions can be obtained. Of course, you need to specify the particular boundary conditions and the initial conditions and so on. So we will look for solutions such as travelling wave solutions, standing wave solutions, etc. And first we would look for first we look for deriving generalized solutions. So the solution procedure is quite simple. We will factorize this wave equation. This is the wave equation, and we assume that d squared p prime by dou x dou t equal to dou squared p by dou t dou x. So we can actually factorize this equation as follows. It is quite simple to work out. So this is the same equation, factorized it. If you expand this equation out, you will get the equation on the top. So then we can have two possibilities. One is dou p by you have the first operator acting on pressure equal to 0, or you can also have the possibility of the second operator acting on the pressure, fluctuating pressure. The second operator acting on the fluctuating pressure makes it 0. So if you look carefully, you can rewrite this as dou p prime by dou x plus 1 over c dou p prime by dou t equal to 0, or we can write dou p prime by dou t plus c times dou p prime by dou x equal to 0. So you can easily see that the c is the characteristic speed, dx by dt equal to c. So the solution, a generalized solution for this would be equal to f of x minus ct. And similarly, if you look here, you can write this equation as dou p prime by dou t minus c dou p prime by dou x equal to 0. So the characteristic speed here is dou x by dou t equal to z. Oh yeah, it should be c, sorry. Thank you. So this would be p prime equal to g of x plus ct. So f is one function, g is another function. Now you can write a general solution as p prime equal to f of x minus ct plus g of x plus ct. So this would be the general solution. Now it is quite easy to convince yourself that this solution actually satisfies this first equation, and this equation actually satisfies the top equation. Now I will just show that. Let's make a change of variables or a transformation that will make things easy. So we say that psi equal to x minus ct. So we say that dou p prime by dou x equal to dou p prime by dou psi into dou psi by dou x. Similarly, we can say that dou p prime by dou t equal to dou p prime by dou psi into dou psi by dou t. Now if you see dou psi by dou x equal to 1 and dou psi by dou t equal to minus c. So if we substitute this in here, I will get so now if I substitute this in the wave equation, what we had was dou p by dou t plus c dou p by dou x equal to 0. So if you make these substitutions, dou p by dou t is nothing but minus c dou p prime by dou psi plus c times dou p prime by dou psi. You can see that this actually cancels this and you will get 0. So therefore f of x minus ct is actually a solution to the wave equation. Similarly, if you follow the same procedure except you use another variable, if you use eta equal to x plus ct, you can prove that g of x plus ct is also a solution to the wave equation. Therefore, the general solution for the wave equation is p prime equal to f of x minus ct plus g of x plus ct. So I must emphasize that f and g are at this stage simply arbitrary functions, and we do not know what they are. They could be any functions, but the specific form of the functions depends very much on the type of initial condition that you use and the type of boundary conditions that we use. So now the big question we have to ask is, what is C? So the next question is, what is the meaning of C? Towards this purpose, let's just take a look at the first solution, p prime equal to f of x minus ct. So if the meaning of this is that as long as you are on the line x minus ct equal to constant, you will see the same pressure. So that x minus ct is some kind of preserved quantity. So if you have a wave shape and it moves to some other place, between similar points this quantity will be preserved. So let us say you are at x1 comma t1 at some time at one instant, and at another instant we are at x2 comma t2. Now if you are on the solution, then we have to make sure that x minus ct is a constant. That's the thing, it's preserved. So now you will say that or t minus x by c, some people write x minus ct, sometimes you can say t minus x over c, whatever. So t1 minus x1 over c equal to t2 minus x1 over c, or we can rewrite this as x2 minus x1 over t2 minus t1 equal to c. So you can really see that t is the time taken by the wave to travel from x1 to x2 in this time interval t2 minus t1. So therefore c is indeed the speed of sound. Now if you are looking at a right propagating wave, now f of x minus ct is a right propagating wave because the velocity of the wave is it's writing on the characteristic dx over dt equal to c, and so it's a right running wave. If you were to write the other solution, you have g of x minus ct. If you look at this solution, what is preserved is or it can also be written as g of t minus x over u of x plus ct. So t1 plus x1 over c1 equal to t2 plus x2 over c2. So what we can see is x2 minus x1 over c equal to t1 minus t2, or x2 equal to x1 minus c into t2 minus t1. That means actually the wave is, here you can see its wave is propagating to the left. So this is a left running wave, whereas in the earlier case we see that the wave is propagating to the right, because we can see that x2 equal to x1 plus c into t2 minus t1. So this is a so called right running wave. So now we can clearly see that why c is the speed of sound. Where? Now we can clearly see why c actually is the speed of sound. Anything else? Okay. So let's look at some more things about the solution p prime equal to f of x minus ct, or g is equal to x plus ct. So this means that along this x minus ct you have a certain shape of the wave, or along x plus ct you have a certain shape of the wave. That means we are having a solution which says that the wave shape is constant, wave shape does not change, the amplitude does not change, only the wave just propagates. So we are looking at a 1D wave only plane wave because we only have coordinate x, so it is a plane wave. So let us look at the features of 1D plane wave. So the amplitude is always either f or g, so there is no attenuation or spreading. And the second feature is that the wave shape does not change during propagation. We will see later on in the course where we will have situations where the amplitude and the shape will change during propagation, but at the moment in this classical case the wave shape does not change during propagation. So the last thing is I want to work out is to work out the relationship between the acoustic pressure and the acoustic velocity. How do we go about doing this? So we can actually work this out by using the momentum equation or the Euler equation. It is linearized version. So we are trying to derive the relationship between acoustic pressure and acoustic velocity for a plane wave. So we use the linearized Euler equation or the linearized momentum equation, which is rho bar dou u prime by dou t equal to minus dou p prime by dou x. So we can do this relation separately for a right propagating wave and then for a left running wave. So let's denote the right propagating wave by plus and the left propagating wave by minus. So we will write dou u prime plus over dou t equal to minus 1 over rho bar dou p prime plus over dou x. So all we need to do is to say that so you can integrate this right hand side with respect to time and you will be able to get the velocity. So we can change the variables to psi equal to x minus ct. Then we can see that dt equal to minus 1 over c d psi. So dp by dx equal to and now if you substitute this in here, what you can get is u plus equal to minus 1 over rho bar integral dou f by dou psi into minus 1 over c dou psi by dou psi. So this would be nothing but 1 over rho bar c integral dou f, which is f over rho bar c if you are starting with initial conditions that are quiescent. So basically we can say that u plus equal to p plus divided by rho bar c. Now if you were to work out this relation for the left running wave, and that is quite easy. So we say that eta equal to x plus ct and we can follow the same procedure and you can then derive the relation. Sorry, it's you follow the same procedure as for integration. You can and then you will get the result. So it's just to so you would get this relation. So there's a minus sign in front of p prime. So in either case, either for a left running wave or a right running wave, the magnitude of the velocity is the magnitude of the pressure divided by rho bar c. Rho bar c is a quantity called characteristic impedance. Now the only thing is, for a right running wave, the velocity, the expression for the velocity is u plus equal to p plus divided by rho bar c. For a left running wave, u minus equal to minus p minus divided by rho bar c. So there is an opposite sign. This is, although it looks strange that there is a different sign, it is quite intuitively obvious. So let us look at a compression wave which is going to your right side. Now if the wave is going to the right side, the gas particle will, if it is a compression wave, the gas particle will move behind the wave to the right. So then the sign should be plus, because you are having the wave also move behind the velocity move also to the positive x axis. So there should be a plus, whereas if the compression wave is going to the negative x axis, then the particle will trail that compression wave to the negative x axis. So it will naturally have a minus sign because it is going into opposite direction. So that's what that's the reason for this left running wave having a minus sign in front of it for the expression for the acoustic velocity, whereas the right running wave has a plus sign or a positive sign before the expression for acoustic velocity. So in general, p plus over u plus equal to p prime minus divided by. So if you take the ratio of the magnitudes, it will always be rho bar c. Now rho bar c is called characteristic impedance of the medium. Different mediums will have different values. For example, air would be the value would be around 400. For water it would be some other value. For example, let us work out. Rho bar c would be typically rho would be, let us say, 1.2 kg per meter squared into speed of sound would be typically 330 meter per second. So you will get approximately 400 kilogram, let's see, meter per minus 2 second per minus 1. So this unit kilogram meter per kilogram per meter squared second, this is called this unit is referred to as Rayleigh, in order to honor the great scientist Lord Rayleigh, who did a lot of pioneering work in acoustics. Now if you are having a, so this is the value for air. Now if you are having another medium water, so you would have rho bar is 1000 kg per meter cube for water. Speed of sound is of the order of 1500 meter per second. So rho bar c would be of the order of 1.5 into 10 power 6 Rayleigh. So you can see that for different mediums the value of the rho bar C, the characteristic impedance is quite different for different medium. So we will stop here at this point. What we did is here, yeah, I put the absolute value sign, so it's okay. So to summarize, what we did is we took the equations of fluid mechanics which we derived in last class, then we made assumptions of linear acoustics. That means we split the variables into a mean quantity and a perturbation quantity. Then we said that the perturbations are very small compared to the mean, so we actually we kept the quantities which are first order in the perturbations, but we neglected everything that is second order or higher, and then we massaged these equations and derived the classical wave equation. Then we actually proceeded to find the solutions to the wave equation, which is as I showed earlier, f of x minus Ct and g of x plus Ct, and then we also derived expressions for acoustic velocity in terms of the acoustic pressure. So we will stop here today. Thank you, have a good day.